About 2 weeks ago, I reviewed this early production model of the Dwarf 3, and a lot of you guys asked me if I could also do a comparison video between the Dwarf 3 and the SeaStar S50, so that's what this video is all about. I'm going to compare the technical specifications between these two telescopes, and we're also going to do some solar, lunar, and deep sky astrophotography using both telescopes. And in the end of the video, I will give you my final verdict.
Not guilty.
Hope you can appreciate that, and let's go.
The Dwarf 3 Smart Telescope is currently priced at $499, not including taxes. In the box, you'll find the telescope itself, magnetic solar glasses for safe solar imaging, a USB 3.0 charging cable, cleaning cloth, and a travel bag for easy portability. However, it doesn't come with a tripod. The good news is that the Dwarf 3 is compatible with any standard camera tripod that uses a 1¼ inch screw, so you can easily attach it to one you already own. The ZWO SeaStar S50 Smart Telescope is also available for $499. For that price, you'll get the SeaStar S50, a solar filter, a sturdy tripod, a carrying case, and a USB-C charging cable. You can find links to ZWO, Dwarf Lab, and reliable telescope shops for both telescopes in the video description below.
About a year ago, I also tested its predecessor, the Dwarf 2, and I really loved the design and the price, but it also came with some significant challenges like noisy astrophotography images, some frustrations to connect and control the Dwarf 2 using the app, and a limited Wi-Fi range. So fast forward 1 year and Dwarf Lab is about to release their latest Dwarf 3 Smart Telescope, which has better optics, a better camera sensor, an updated app, and more.
Let's compare the optics. The Dwarf 3 features a 3.4mm wide-field lens and a 35mm telephoto lens with extra low dispersion glass to reduce diffraction spikes and chromatic aberration for sharp images. The telephoto lens has a 150mm focal length, and the Dwarf 3 has an 8.3-megapixel Sony IMX678 sensor that is optimized for low light conditions with Starvis 2 technology. The Dwarf 3 offers a 2.93 by 1.65 degree field of view that's about 6 times the width of the Moon, making it great to capture large objects like the Andromeda Galaxy. With an image scale of 2.75 arcseconds per pixel, it's slightly above the ideal 1 to 2 arcsecond range for deep sky imaging, but still close enough so it should deliver solid results. The SeaStar S50 features a larger 50mm aperture and a longer 250mm focal length triplet refractor design, providing slightly better light gathering and greater magnification capability as compared to the Dwarf 3. However, the S50 uses an older 2-megapixel Sony IMX462 camera sensor with earlier Starvis technology for low-light imaging, while the Dwarf 3 boasts an 8-megapixel sensor with newer Starvis 2 technology. The SeaStar S50 has a narrower portrait field of view of 0.7 by 1.3 degrees, which fits the width of just one full moon within its view. It does have a slightly better image scale of 2.39 arcseconds per pixel, which should give the S50 a slight edge in clarity for deep sky objects.
When you're going to image the sun, always remember to never look directly into the sun, as you might go blind, and always put a solar filter in front of your telescope. Now, for both these telescopes, solar filters are included in the original purchase. This is the solar filter you can use with the SeaStar S50, and these super duper magnetic solar filters you can use with the Dwarf 3. So let me show you how to put these on.
Installing the solar filters on both telescopes is pretty straightforward. For the SeaStar S50, you simply place the solar filter in front of the lens like this. Just be cautious, as there might be some frictions when you attach it. For the Dwarf 3, you can easily attach the magnetic solar filters in front of the two lenses like this, and you're all set. It's crucial to level the telescope tripod and point it roughly at the sun to kick off your solar imaging session with the SeaStar S50. You'll also need to download and install the SeaStar app, which is available for both Android and iOS devices, but not for Windows. For detailed instructions on installation and connecting to the SeaStar S50, check out my original review video. Once connected via Wi-Fi, I selected the Solar System tab on the app's main screen, tapped on the sun, and hit Go Gazing to begin my session. The app reminded me to place the solar filter in front of the telescope before starting the session. After tapping on Installed and shooting, the Seestar S50 located the Sun in under a minute. With solar maximum happening in 2024, I was very excited to see numerous sunspots on display. After finding the Sun, I tapped the Target Correction button in the top right corner to initiate tracking, keeping the Sun centered on my screen. I then used the 2x the Zoom button to focus on some sunspot regions and selected Autofocus. As expected, the Seestar S50 perfectly focused on the sunspots. I even zoomed in to 4x to ensure the autofocus was spot on. You can swipe the screen to adjust the view. The Seestar app allows you to take photos and videos. I recorded 2 videos, the first one in MP4 format without selecting the RAW option. Here's a short clip of that 1-minute MP4 video, clearly showing the sunspot regions. If you need to adjust the brightness, you can easily do so using the plus/minus button. I decided to keep the brightness as is, selected the RAW option, and recorded a 2-minute video in high-quality 16-bit AVI format, ideal for advanced astrophotographers looking to stack and process images using software like AutoStacker, Registax, WaveSharp, or AstroSurface. After recording a 2-minute video, I concluded the session. Now let me show you a single image of the Sun captured through the Seestar S50. And here's the stacked and processed photo of the Sun from that day, where I slightly sharpened the sunspot regions and adjusted the color of the Sun to a more yellowish tint. For a $500 smart telescope, I really like the picture. Just like with the Seestar, I needed to level the Dwarf 3 and point it roughly at the Sun before starting a solo session. After that, I simply turned on the Dwarf 3 and connected to it via Wi-Fi after downloading the Dwarf Lab app available on any Android or iOS device. For a more detailed explanation, check out my separate Dwarf 3 review video. Once connected, I tapped the photo icon, which brought up the control panel. Using the joystick-like controls on the bottom left, I centered the Sun in the telephoto lens using the wide lens view for guidance. I adjusted the slew speed with the speed dial on the right side of the screen. Once the Sun was centered in the telephoto view, I tapped on the telephoto view in the top left, switching from the wide view to telephoto, which I found to be a really cool feature. I then used autofocus on the right to fine-tune the focus on the Sun and pinched the screen to zoom in, where I could see the same sunspot regions as I did with the Seestar S50 a few minutes ago. I took a quick photo of the Sun in photo mode, and here's that picture. After that, I initiated the Sun tracking mode under the Function tab, which prompted me to ensure the tripod was level, solar filters were on, and the Sun was centered in the telephoto view. As I had everything set, I tapped Done, and the Dwarf 3 started tracking the Sun automatically. I zoomed in again and re-initiated autofocus to make sure I had the best possible focus on the sunspots. After that, I switched to video mode to capture a 1-minute video of the Sun. Here's a short snippet of that video. Next, I switched to Astro mode, which offers a more advanced way to capture and stack images of the Sun. I checked the exposure settings under the Function tab for the telephoto lens, which were automatically set to 1/800th of a second at 0 gain using the daytime Vis filter. Then I went into the settings in the Function menu and instructed the Dwarf 3 to take 300 fits images of the Sun. I left stacking, 4K, and AI enhancement enabled and tapped the photo button. The Dwarf 3 then started taking pictures and live stacking the Sun on the screen, which was really cool to watch. Once the 300 fits images were taken, I ended the session. Here's the automatic stacked image of the Sun that the Dwarf 3 produced. And here's my edited version after applying a bit of sharpening. When comparing both the video and final images from the Dwarf 3 and the Seestar S50, I personally prefer the Seestar S50 for its slightly better clarity on the sunspots. However, the difference is minor and I could only really notice it when zooming in on the sunspots. Let me know in the comments which one you prefer and what you think of the results.
Alright folks, I'm going to take these solar filters off and wait until nightfall to also do some lunar and deep sky astrophotography using the Dwarf 3 and the Seestar S50.
As night fell, I set up both the Dwarf 3 Smart Telescope and the Seestar S50, aiming them at the rising waxing moon. I started with the Dwarf 3 this time, connecting it to my smartphone over Wi-Fi. Using the virtual joystick and the speed dial, I positioned the moon in the telephoto view, first relying on the wide-angle lens to help center it. Once the moon was centered, I switched to the telephoto view and used autofocus to lock in the focus. Capturing the moon with the Dwarf 3 feels very similar to imaging the Sun. Under the Functions menu, I selected Moon Track Mode, which prompted the telescope to warn me to level the tripod and ensure the moon was centered in the telephoto view. Since I'd already done that, I simply pressed Done and the Dwarf 3 began tracking the moon. I zoomed in further and used autofocus along with the manual plus and minus keys to fine-tune the sharpness. This time I switched directly into Astro mode to capture the moon. Under Functions, I saw that the shutter speed was automatically set to 1/125th of a second at 0 gain with the Vis filter active. I kept the default exposure and gain settings and moved to the Settings menu to capture around 220 fps images with the default 4K, live stacking and AI enhanced features enabled. Just like in solo mode, the Dwarf 3 began live stacking the images of the moon in real time, which was fascinating to watch. After 220 images, I wrapped up the session. Here's the automatically stacked picture of the moon. I did a bit of post-processing to desaturate and sharpen the image, resulting in this final image. Not bad at all, don't you think? Next, I switched to the Seestar S50 to capture the moon. Using the Seestar app, I selected the moon under Solar System mode and tapped Go Gazing. The app prompted me to level the tripod using real-time guiding circles, ensuring they were within 2 degrees of each other. After leveling the tripod, I tapped Go Gazing again and the Seestar automatically slewed to the moon. Once the moon was in view, I activated the tracking feature from the top right and the Seestar began tracking the moon automatically. I zoomed in by tapping the 2x zoom button at the bottom of the screen, enabled autofocus and placed the green rectangle around Copernicus crater. The Seestar autofocused perfectly on the moon. I then switched to 4x zoom to ensure the craters were in sharp focus. After that, I captured a photo by pressing the photo button, and here's the resulting image of the moon. I also recorded a 2-minute raw video and used AutoStacker and WaveSharp to stack the frames from that video and sharpen the picture. This resulted in this enhanced image of the moon. When I compare my individual photos and the stacked and processed images from both the Seestar S50 and the Dwarf 3, I noticed that the Seestar S50 offers just a bit more clarity, likely due to its larger aperture. However, the difference is really small and only noticeable when zooming into the craters. What do you think? Do you agree? Let me know your thoughts in the comment section below. Over the past few weeks, I've been busy capturing different deep sky objects using both the Dwarf 3 and the Seastar S50 for this comparison video. Let's start with the Dwarf 3. One standout feature of the Dwarf 3 is its EQ mode, which allows for polar alignment. Polar alignment is the process of aligning a telescope with the Earth's rotational axis by pointing it toward the north or south celestial pole, depending on the hemisphere you're in. This alignment allows the telescope to track celestial objects smoothly as they move across the sky, compensating for Earth's rotation. Proper polar alignment is crucial in astrophotography to avoid field rotation, star trails, and ensure sharp, longer exposure images. The polar alignment procedure for the Dwarf 3 is quite different, and it took me quite a bit of time to figure out. Let me walk you through it. Instead of pointing the Dwarf 3 north toward Polaris like most alignment procedures, I had to point the Dwarf 3 toward the south with its lenses angled forward. Again, pointing south. Then, I needed to adjust the tripod's tilt to match my latitude, which is 52 degrees here in the Netherlands. Using the Dwarf Lab app, I focused on the stars first by adjusting the shutter speed to about 1 second and the gain to about 100. After that, I tapped on EQ mode in the function settings. EQ mode first explains how to set up the telescope, but I find that explanation a bit confusing, to be honest. After that, EQ mode gave me helpful directions to fine-tune the tilt and the left-right position of my tripod until I was within 2 degrees of proper alignment. Once aligned, I could track deep sky objects for up to 60 seconds. If this process feels like too much hassle for you, you can skip this step, but keep in mind it will limit your exposure time to around 15 seconds to avoid star trails and field rotation. Once you've completed the polar alignment procedure, the next step is to calibrate the Dwarf 3 so it knows precisely where it's pointed in the night sky. To do this, go to Astro Mode and find Calibration under Functions in the bottom right. The process is automatic, but make sure the Dwarf 3 is focused on the stars with a shutter speed of 1 to 2 seconds and a gain of around 100. Hit Calibrate and the telescope will go through several automatic steps to complete this process. After calibration, you can use the Virtual Sky Atlas, also found under Function in Astro Mode. After searching the Andromeda Galaxy in the database, I clicked on the photo icon in the top right and the Dwarf 3 automatically flew to the galaxy, perfectly centering it within its field of view. As I was still figuring out EQ mode at the time, I limited my exposures to 30 seconds and put the gain to 50 with the Astro filter selected. I decided to take 300 fits images with stacking, 4K and AI Enhanced selected. After hitting record in Astro Mode, the Dwarf 3 warned me I didn't have any dark frames and I could take them right there. Dark frames are images taken with the same camera settings in terms of shutter speed and gain as your light frames, with the telescope's lens or camera covered, capturing only the inherent noise from the camera sensor. They are important in astrophotography because subtracting dark frames from your images reduces sensor noise and hot pixels, resulting in cleaner, more accurate final images. As I was already pointed at Andromeda and eager to image the galaxy, I skipped that step, hoping that lowering the gain to 50 and the Starvis 2 technology of the IMX678 Sony sensor would already lower the noise to an acceptable level in my light frames. The Dwarf 3 immediately began taking 30-second exposures and displayed a live stack, which is a really cool feature. I noticed that the satellite left a streak in my stacked image, but as the stacking progressed and multiple images were added, the streak gradually disappeared. Keep in mind that the Dwarf 3 also saves each individual fits photo separately, so if you don't like the automatically stacked image of the Dwarf 3, You can also manually stack the individual bits files, omitting the ones you don't want to use, or use advanced stacking algorithms to reject such anomalies. After stacking 300 photos, I ended the session. Here's the automatically stacked image from the Dwarf 3. And here's my processed picture of the Andromeda Galaxy, where I stacked and processed the photos myself using PixInsight. What do you think? The C-Star S50 doesn't have a dedicated polar alignment procedure like EQ mode, so its default exposure time for capturing deep sky objects is limited to 10 seconds. However, you can extend this to a maximum of 30 seconds in the advanced features settings. You also have the option to save each individual photo or only the stacked image in those settings. The C-Star app includes a dedicated section called Stargazing, which features various categories like galaxies, nebulae, star clusters and more, and a very nice virtual sky atlas. I noticed that the Andromeda Galaxy was suggested under current best objects to photograph. I scrolled through the Galaxy database, found M31, tapped on it and got more information about its position in the night sky, and then I hit Go Gazing. After that, the C-Star S50 handled everything automatically, engaging in horizontal calibration and initialization procedures, which took about 2 minutes before it began live stacking the 10-second images. I collected about 2 hours of data, and at that point I noticed some field rotation at the edges of the picture, and I decided to stop the live stacking session. Here's the automatically stacked image from the C-Star S50, and here's my version that I stacked and processed using PixInsight. You can clearly see the issue. The field of view of the C-Star S50 is too narrow to capture the entire Andromeda Galaxy. When I overlay the images from the Dwarf 3 and the C-Star S50, the difference becomes apparent. Let's move on to the Eastern Veil Nebula located in the constellation Cygnus. The Veil Nebula is an emission nebula rich in ionized hydrogen and oxygen gases, so I use the internal duo-band filter, which captures light specifically at those wavelengths while blocking out light pollution in my Bortle 8 light-polluted city sky. Since I polar aligned the Dwarf 3, I opted for 60-second exposures at 100 gain and began capturing the nebula. After taking 225 photos, that's 3 hours and 45 minutes of total exposure time, I wrapped up the session. I also captured the same nebula a while back with the C-Star S50 using an earlier version of the app. Thanks to the portrait orientation of the C-Star sensor, it fit perfectly within the field of view. Just like with the Dwarf 3, I used the internal duo-band filter on the C-Star to capture the nebula, which isolates the ionized hydrogen and oxygen wavelengths while reducing light pollution. The C-Star S50 took 10-second pictures, and after about 1.5 hours, I had to cancel the session due to field rotation. Here's the automatically stacked image from the Dwarf 3. And here's the version I processed using PixInsight. Here's the automatic image from the C-Star, and here's my processed version. Let's zoom in on the Eastern Veil Nebula using the Dwarf 3 image. I'll now overlay the C-Star S50 image. Aside from some color differences due to my processing preferences, there isn't a huge variation between the two. I feel this is important to mention because some folks assume that the C-Star's 2-megapixel camera sensor would result in a lower resolution picture as compared to the Dwarf 3's 8-megapixel sensor. As this comparison shows, resolution mainly affects how large your field of view is in astrophotography and not necessarily the level of detail you get in your image, which depends much more on the aperture of your telescope, the image scale, and astronomical seeing conditions. I also imaged M45, the well-known Pleiades cluster, using both smart telescopes. With the Dwarf 3, I used 30-second exposures, a gain of 60, and selected the internal Astro filter. In total, I captured 250 fits images, giving me just over 2 hours of total exposure time. Here's the auto stack the Dwarf 3 produced. This time, I only used Photoshop Lightroom to boost the colors a bit. I also captured M45 with the C-Star S50 using the default 10-second exposures. After 1 hour and 50 minutes, I wrapped up the session. Here's the stacked image the C-Star S50 produced automatically. And here's the version after some basic processing in Photoshop Lightroom. When comparing the two, it's clear that the C-Star S50's smaller camera sensor captured only part of the star cluster. However, with 10-second exposures, the bright stars are less overwhelming, and I could see more nebulosity detail around the stars compared to the Dwarf 3's 30-second exposure stack. Now obviously, I could have taken 10-second exposures with the Dwarf 3 as well, but I want to highlight an important point. Shorter exposures can be beneficial. They reduce potential tracking issues and they prevent oversaturation, which is a big plus when you're shooting in a bright urban environment like me. Let's move on to the final comparison, the Heart Nebula. This nebula is massive, spanning about 2.5 degrees across in the night sky. The Dwarf 3's landscape sensor was almost perfect for capturing it in one photo. Since it's an emission nebula, I used the internal duo-band filter and, being polar aligned, I went with 60-second exposures at 100 gain. I took 250 fits photos with live stacking enabled. I also imaged the Heart Nebula with the C-Star S50, sticking with its default 10-second exposures. After about 90 minutes, I ended the session when I noticed some field rotation in the corners of the stacked image. Here's my automatically stacked image from the Dwarf 3, and here's my processed version using PixInsight. This is the C-Star S50's stacked image, and here's my PixInsight processed version. Clearly, the C-Star S50 could only capture the core of the Heart Nebula, also known as Melote 15. Let's do a quick overlay for comparison. The C-Star's shorter 10-second exposures produce slightly tighter stars and a sharper image of Melote 15 compared to the Dwarf 3's 60-second exposures. That said, I do love the Dwarf 3's ability to capture more faint nebulosity thanks to those longer exposures, and I do love the wide field of view. Both the Dwarf 3 and the C-Star S50 can connect to your home Wi-Fi network, allowing you to control the telescopes from your living room while the telescopes handle the imaging outside. The Dwarf 3 has an STA mode under Connection Settings to connect to your network, while the C-Star S50 features a Station mode under its Wi-Fi settings. In terms of battery life, the C-Star S50 has a 6000 mAh battery, while the Dwarf 3 boasts a larger 10,000 mAh one. Both can run for hours and can be recharged using a USB-C cable even while in use. The Dwarf 3 includes a daytime vis filter, a nighttime astro filter for near-infrared light, and a duo-band filter for emission nebulae, while the C-Star S50 also has an internal duo-band filter. For storage, the Dwarf 3 offers 128GB and the C-Star S50 provides 64GB. so plenty of room to store your videos and FITS files. However, neither telescope can capture detailed surface images of planets. You need a much bigger telescope for that. When it comes to daytime use, the Dwarf 3 is also marketed as a nature and wildlife photography device, allowing you to take stunning photos, track moving objects and create time-lapses of panoramas, as I demonstrated in my earlier review video of the Dwarf 3. The SeaStar S50 also features a daytime scenery mode that enables you to capture beautiful daytime images, videos and time-lapses as well. Both telescopes are compact and lightweight, with the SeaStar S50 weighing only 2.5 kilograms and the Dwarf 3 at just 1.3 kilograms. This makes it incredibly convenient to take them along on your weekend getaways or holiday trips. So let me give you my final thoughts. ZWO's SeaStar S50, introduced in April 2023, remains one of the most affordable smart telescopes on the market today. Its app offers full automation, making it perfect for beginners who want to easily capture the sun, the moon, and deep sky objects without diving into the complexities of astrophotography. The advanced storage options, including AVI RAW videos and FITS files, also give more experienced astrophotographers flexibility in post-processing. The 50mm triplet design delivers sharp images, though the 2-megapixel sensor does limit its field of view for larger objects. While ZWO is testing a mosaic mode, keep in mind that capturing mosaics doubles the exposure time, similar to what I reviewed in the Vespera 2. And just as I was working on this review, ZWO teased a new S30 smart telescope. So I'm very excited to see where they go next. As for the Dwarf 3, Dwarf Lab has made significant improvements across the board as compared to earlier versions of their Dwarf telescopes, from the optics to the camera sensor and the app. It's a highly versatile telescope for both day and nighttime use. The new EQ mode lets you track objects for up to 60 seconds, allowing for longer exposures and less noise, revealing finer details in your images. The wide field of view with the newer IMX678 camera sensor with Starvis 2 technology makes it ideal for capturing larger objects in a single frame. While the Dwarf 3 app has seen major updates, it may still take a little time to get fully comfortable with the app. But with a bit of practice, it becomes second nature. Both telescopes offer fantastic value depending on your needs, and I'm excited to see how they continue to evolve. Guys, I've spent way too much time editing this video, so if you liked it, go ahead and smash that like button. Don't forget to subscribe for more updates, and if you really want to help me out, join the channel to support future videos and binge watch my free planetary imaging course. As always, may your skies be clear, and see you in the next video.